All right, so we're moving on to 15.6 now. And up until this point, throughout chapter 15, our focus has been on double integrals, which has been our generalization of the integral to functions of two variables, things of the form f of x, y. Now what we're going to try to do is move that up to a generalization of the integral to functions of three variables, functions of the form f of x, y, z. So to sort of think through how we came up with the idea of a double integral, we looked at what we did for single variable integrals, starting all the way back where we define a Riemann sum. And in particular, we looked at the part of the domain of a function that we integrate over. So in the case of calculus 1, calculus 2, where you're looking at a function f of x, where there's only one variable, the domain of that function is a subset of the real numbers, and that subset will live on the x-axis when we look at the graph of that function. Typically, the subsets that we look at, that we're integrating over, are intervals. So in the case of a definite integral of a function of one variable, we integrate over intervals. In the beginning of chapter 15, we looked at what that would look like in the case of a two-variable function. So in the case of a function of x and y, the domain of that function is a subset of the xy plane. The domain looks like points, sets of points with an x and a y coordinate. So we began by looking at what happens if we take an interval on the x-axis and an interval on the y-axis. Together, those create a rectangle in the xy plane. And so we integrated over rectangles in the case of double integrals. And then we saw that we can integrate over more general regions as long as the region lived in the xy plane, because that's where the domain of a function of x and y would live. Now, kind of moving that up to one more dimension, if we're looking at functions of three variables, the domain of those functions are subsets of three space. So they contain ordered triples. So now we need to come up with a way of integrating functions that have three variables where their domains look like solids now, instead of plane regions, like in the case of double integrals. So to think this through, we're going to take a look at what happens if we have a function of three variables, x, y, and z. And if we were to take an interval on the x, y, and z axes and look at where those intervals all intersect, they're going to intersect in a... or I shouldn't use the term intersect. That's technically not the right terminology. I should be using the term Cartesian product. That's what this is. But nonetheless, those three intervals will go together in a sense to create a rectangular box like this. You can see that the interval on my x-axis gives it a width. On my y-axis, it gives it length, and the interval on the z-axis gives it height. But it creates a rectangular box. This box is not the graph of the function that we want to integrate, but instead it's a subset of the domain of the function that we want to integrate. We can't visualize the graph of f of x, y, z, because remember, a three-variable function would require a four-dimensional graph. There's a fourth variable that we use as the dependent variable here. We can't visualize that. So the regions that we draw throughout this section and the later sections in chapter 15 are not graphs of the integrand. Instead, they're solids representing a region that we're integrating over. So now, how then do we use this to come up with an integral? Well, rather than go through the full derivation that we did in 15.1 for double integrals, we just bear in mind that we're kind of following the same logic, the same reasoning as in that section, but including one more variable in that derivation. So what we want to be doing is taking our solid region, our solid box that's given by these three intervals on our x, y, and z axes, and breaking each of these intervals up into several sub-intervals, the same way that we do with single variable integrals, with double integrals. Only this time, breaking all three of these intervals into sub-intervals partitions this rectangular box into a bunch of little sub-boxes, which we're going to denote B, I, J, K. The I, J, K are referring to the ith subinterval on my x, the jth subinterval on my y, and the kth subinterval on my z. So if I were to take one of those little boxes and sort of zoom in on it like we do here, we would see that it has length, width, and height, which I'm going to denote by delta x, delta y, and delta z. With that in mind, I can see that the volume of this box, which I'm going to write next to this, I'm going to call that delta v, is equal to delta x, delta y, and delta z. It's the product of those three. Okay, so with that in mind, if I wanted to try and come up with some sort of Riemann sum, I would first make a note that the ijk little sub box here could be written as a Cartesian product this way of these little subintervals. That represents the set of all points contained inside that box, not just on the surface, but inside. And mimicking what we do in the case of double integral, if I have some function f of xy f of xyz that's defined over that box, then after dividing it into all these little sub boxes, I pick a single sample point within each one of those sub boxes called xijk star, yijk star, zijk star, and evaluate my function at each one of those, multiply by the volume of each little sub box, and then sum all of those products for one term for each of the sub boxes in this larger box. What that creates is a triple sum, kind of like how we had double sums that led to double integrals. This, when I take a limit as L, M, and N all go to infinity, is what gives me a triple integral. So here's our definition for a triple integral. The triple integral over the solid, I'm going to be calling these solids, the solid B, which is this entire box here in this diagram, of f of x, y, z, dv. Notice we're using a dv here instead of a dA. dA was because we were looking at a region that had area, but now we're looking at a solid that has volume. V is for volume, and you can see that the delta v is becoming that dv there. It's equal to the limit as that triple integral goes, as that triple integral, I'm using the wrong terms here, as the triple sum of this function as L, M, and N all go to infinity. So just like with double integrals, there's an extension of Fubini's theorem for that. Fubini's theorem for double integrals, we kind of get a little too attached to only one part of that theorem, where we say that the theorem means that you can perform an iterated integral with rearrangements of the order of integration as long as this function is continuous on the box B or on the region D if we're talking about double integrals. But Fubini's theorem also is the statement that these triple integrals can be evaluated as iterated integrals at all. So Fubini's theorem also is telling us that when we evaluate these triple integrals, we can do so in the form of an iterated integral. So, and then in addition to that, we could rearrange the order of this integration. So let's start with an example where we want to find the triple integral of the function xy plus z squared dv, and E is the set of all points satisfying these three conditions. X is between 0 and 2, y is between 0 and 1, z is between 0 and 3. So that's going to be, these are going to create the limits of integration that I use for my iterated integral. Let's go ahead and evaluate this. So I can do this in any order that I want, but I'm going to do dx, dy, dz. I'm going to integrate with respect to x, followed by y, followed by z. And let's just see what that gives us. So that means my outer integral will use the limits from my z, 0, 3, followed by my y, 0, 1, followed by my x, 0, 2. Okay, and then the function looks like x, y plus z squared. And the dv is going to split up into a dx, dy, dz. And again, that order can be changed up. But if you change the order of your dx, dy, and dz, you have to also change the order of these integrals here to match that. So to begin with, I'm integrating my function with respect to x first. This is going to give me 0 to 3, integral from 0 to 1. Okay, this will become x squared y over 2. X squared y over 2 plus z squared x from 0 to 2 dy dx. Oh, sorry, dy dz, not dx. Careful with that. All right. Remember that these limits of integration are x values, so I'm substituting values in for x. Plugging 0 into either one of those is 0, so really it's just the 2 that matters. This becomes 2 squared y over 2, or 4y over 2, which simplifies to just 2y. This will become plus 2z squared. dy dz. Okay. Next up, we're integrating with respect to y. So 2y becomes y squared. This becomes 2/3 z. Oh, whoop. Caught myself just then. It does not become 2/3 z cubed, doesn't it? Because it's integrating with respect to y. So let's fix that. It's going to be plus 2z squared y. Caught myself. All right. That just goes to show, make sure you're paying attention to what you're doing every step of the way. It's very easy to find yourself integrating with respect to the wrong variable if you're not paying attention. So, okay, integrated with respect to y. Once again, the 0 down here makes this simple. I just need to plug the 1 in and we're good to go. So, plugging the 1 in for my y's now. 1 squared is just 1. 2z squared times 1 would just be 2z squared, so plus 2z squared. And then we're going to integrate with respect to z next. Okay. One last integral to evaluate. We're integrating, actually, let's just go straight to the answer here. Integrating with respect to z, so that 1 is going to become a z. This will become plus 2/3 z cubed. There's my 2/3 z cubed. This goes from 0 to 3. Okay, again, the 0 is not going to matter. So this will become a 3 here. This will become a 3 cubed, which will cancel with this 3, giving me a 3 squared. That's 9 times 2, that's 18. So plus 18. And I get a final answer of 21. Whoops, there you go. I have to remember to scooch that up. Okay, so that is as simple, or just about as simple, as a triple integral can be. And yes, it does seem like a lot of steps, but each step is just a single definite integral that we evaluate kind of one step at a time. This is going to get a lot more involved, though, because the types of regions that or the types of solids that we're going to be looking at in this section primarily are not nice boxes like this. So in the next video, we're going to talk about sort of the generalization of type 1 and type 2 regions that we talked about in 15.2. We actually have 3 different types, and they're type 1, type 2, and type 3 solids. So the next video is going to get much more interesting.